Hey everybody, since any prime factorization contains exponents, it makes sense to consider the connection between a radical notation, a certain type of radical notation. Let's say if we have um, the nth root of an expression A. Now, whatever this expression is, you can think of an exponent of 1 as being right here. Okay? And so a lot of people prefer rational exponents. And so that's what we're going to write down right here. And you'll see, some of you can probably almost solve this one by inspection. But this particular rational exponent radical notation relationship proves to be quite useful here. And again, there's exponents in this prime factorization, and 400 is the only numerical radicand we see. So let's move along and see how this goes. Okay, so by the splitting property of any radical, that's exactly what I did right here. I just split it apart. 2 to the 4th, 5 squared got split. Okay, now this also is the rational exponent form of this radical notation form. This is the rational exponent form of this radical notation form. Okay, now if you take a look right here and compare this to what this equation is equal to, let's see what happens. All right, so this would be equal to, now y'all, we're going to use this conjunction right here where you have the reciprocal of n over here as your rational exponent. Okay, so what we would have right here would be x over 6. Now perhaps I should put this in parentheses. X over 6 raised to the, now look, we're using, okay, this part right here would be behaving like the a right here, right? Okay, so notice it's the reciprocal of this index. Okay, so you see this will be 4 over x. All right, folks, isn't that kind of neat? That's this is a reciprocal connection. This is the index. The reciprocal of the index appears in the rational notation form. Okay, now in a similar fashion, what are we going to have right here? We're going to have x minus 7, okay, raised to 2 over x. Now, folks, now we're in a position to actually solve this by inspection. Notice that everything, we have a 4 over x here, a 4 over x here, a 2 over x here, a 2 over x here, right? So by inspection, we know that x minus 6, we know that x minus 6, okay, has to equal to 2. It's kind of neat, isn't it? See right here, folks? This x over 6 has to equal to this base, which is 2, since these are the same two exponents here, right? Okay, so that implies that x is equal to 12. Just like that. Now, you can check the rest of them, but if x were 12, this would be 2. If x is 12, this is 1/3. Okay, but that's the cool thing about this problem. We've already solved it, and you could have solved it in any of the locations. Also, if you'd have wanted to, you could have just looked here at 5. Okay, you could have equated x minus 7. Okay, x minus 7. This x minus 7 right here matches up with this 5. Okay. And so we also get x equals 12, which, you know, it's nice to see that it's consistent. And you can check it in the other spots too. But anyway, that's the solution to this question, folks. Now let me know if I'm overlooking anything. This may be slightly too mechanical or formal or whatever. There's probably some of you with enough experience at this to where you just look at this and get the answer. I'm not one of these people. The prime factorization is required. I think it's very useful to think of it in terms of rational exponents. And then this property here is really the part that could stump somebody unless they know some other way. But in any event, the solution to this problem is x equals 12. And you can go back in. I'm not going to go back in and check it, but there's none of the, we haven't broken any rules of exponents or radicals, so this has to be the solution. Okay, thanks for viewing.